All right. Well, thank you for your patience while I get this all straightened out, but it's going to work so nice once I get it all, comfortable with everything. All right. So today we're going to be talking about Chapter 1. And the notes that I'm doing right now are going to just be based on the lessons. So if you go and look at the Lessons tab in the content library, or if you downloaded the book already, which again, you can do that, or you can just look at the stuff in the content library. Either place has the same information. The content library, I'm just going to add like one chapter at a time. The book has everything all at once, so but it'll all be there eventually. Basically, all I'm doing with the notes is using a lot of the same examples and kind of just talking through the kinds of the things that would be covered in the lesson. So we're just basically going to have a conversation about the same material that's here. So again, if you're wanting to go get some more detail on something or want to hear it in a slightly different way, you can always go back and look at the lessons and look at the examples and read through and all that kind of thing. Okay? So I won't be doing things that are verbatim from the lesson per se. Like some of the definitions might be slightly reworded or whatnot, but it's just trying to have a conversation about what we're learning. Okay? And again, I'm sorry if I'm over-explaining things, but I think it's helpful, especially at the beginning of the year, to get a feel for like where else you can look if you didn't, if you don't know what's going on or whatever. Okay, so Chapter 1 is about functions and graphs. So we're not really going to start any trigonometry here in the first chapter. Most of these ideas that we're going to see in the first chapter are going to be recycled from the beginning of your Algebra 3-4 class last year. So a lot of this stuff should feel pretty familiar, and we're not going to, super belabor some of these points, especially if after doing some examples you guys feel like, oh yeah, I remember kind of doing this. It's not a big deal. So today we're going to try to do the first two sections. So the first section, 1.1, is about functions. And do we remember the definition of a function from our algebra course last year? I know it was the beginning of the year that you talked about the definition of a function, so it's been a while. Does anybody remember the definition or something close to it? Again, I don't expect it to be verbatim perfect. Yes. Good. So she says an input with only one output, which is a very reasonable, practical working definition for what we mean by a function. We're going to give a more formal definition here, and in mathematics, often you're going to want a conceptual definition, let's see, it's Bridget. No, I'm in the wrong period. It is Krista, as Krista's described for us. And then at times you're going to need the really technical definition. The place the technical definition comes in handy is if you actually are trying to prove something, or if you're trying to construct a framework and develop a system like we are kind of doing here. But oftentimes when you're actually thinking about things or doing the problems, the practical, the working definition is going to be more useful to you. So it's important to kind of think about it both ways. What is the technical definition, and then what is this really just saying? All right, so Okay. So our technical definition, a function from a set D to a set R is an assignment, or sometimes we refer to it as a map or a pairing, such that every element in D is assigned to exactly one element in R. Using Krista's description here, the D is our set of inputs, and the R is our set of outputs. Now I chose the letters D and R as the names for our sets here for a reason. What do we call the set D? The domain. And what do we call the set R? The range, right? So the set of all input values is the domain. That's the D above. The set of all, forgot the word input there. Output values is the range. That's that R from above. What do we call, or do you remember the name that we give for just any kind of mapping between two sets, whether it's a function or not? Like there's a more generic term than just function. Starts with an R. Relation, yeah. So a relation is just any kind of pairing between two sets or mapping between two sets. A function has this specific property that everything in the domain gets used, and each of those things go to only one place. The idea here with a function, the power behind it, is you want it to be deterministic. That means it's like well-defined. So if you do if you put the input of 1 in, you're guaranteed to just get a single result. You don't want to be able to put 1 into your function and get 2 answers back, because how do you decide which answer is the one you want? It's not entirely clear from that kind of a setup. So there's lots of different ways that we can represent a relation or a function. One of those ways that we can represent them is with a mapping diagram. So a mapping diagram is like a visual. So usually we draw 2 ovals, one to represent the set for the domain and one to represent the set for the range. And then we'll write in some elements inside of those sets. And then we'll just draw some arrows that signify how these, or what the pairing is, or the mapping, or the assignment of x's onto y's. So if I look at this mapping diagram, and we want to ask, is this a function? What do you guys say? Yes, right? So the 2 things we look for is we look to make sure everything got used in the domain. So there are 3 x's in the domain, and each of them is being paired with something else. And then we have to check to make sure that each of these has only one arrow originating from it, right? That it can only go one place. It has to be used and used just once. So those are the 2 things we're really checking. Okay, let's look at another example. Okay. And what about this? Is this a function? So I heard some yeses and some no's. So take a minute and think about it. Reread the definition for what it means to be a function, because it seems like, some people saying one thing, some people saying in the other. What do we think now? No. Good. What's the problem? Yeah, not every x has an assignment. Could we turn this into a function? Yes. And the way we do that would be just to restrict the domain so that we're only caring about x1 and x2. And this is what we do often last year in your algebra course, right? Technically speaking, if you're talking about all real numbers, like a rational function wouldn't be a function because every place where there's a vertical asymptote, you have an x that doesn't get used. What do we do in those cases? Well, we just restrict the domain and say, okay, the domain is everything except these places where there's a vertical asymptote at. And now I have a function again, right? So you kind of remember doing that in your Algebra 3-4 class. And that, I mean, rational functions weren't the only ones where you had a restricted domain. Most of the things you talked about in second semester, the domain wasn't all real numbers, whether it was a radical function or a logarithmic function or a rational function. All of these things had restricted domains. Does that make sense? Okay. And let's look at one more example. Yes, of course. Is this a function? So some people have said yes, some people have said no. Take a reread through that definition. Yes, this is, right? When you're looking at a function, the only thing that you need to look at is the domain, right? So everything got used, and each individual item in the domain only goes to one location, right? Does it matter that some of them go to the same location? No, not in terms of whether it's a function or not. Now, a function where each x goes to a unique y has a special name. That kind of function is called one-to-one. You might have talked about that last year when you talked about inverses. So one way you can predict whether a function's inverse will also be a function is just by checking if the function is one-to-one. So if you have a one-to-one function, its inverse is guaranteed to be a function. If that function is not one-to-one, like this last example is not one-to-one because you have two x's going to the same y, when we find its inverse, it would not be a function. Because that y that has two x's going to it, when we invert it, that y becomes an x that goes two different places. Okay with that? So again, trying to connect these back to things we talked about last year in your Algebra 3-4 class. Because the wonderful thing about mathematics is it kind of builds on things that you've done before. And it's been a whole summer, so I know that like some of this stuff got foggy, which is why we're kind of going back and rehashing and reviewing and all that sort of thing. Okay? So we can represent a function with a mapping diagram like that, but that's really kind of a rather abstract and not very, not very practical way of representing a function, because oftentimes a function, the domain is got an infinite number of values in it, right? So that's not very satisfying. So what if we, another way to represent a function would be with an equation. So let's ask, does y equals x squared plus 2 define y as a function of x? So when we write the phrase like y as a function of x like this, which variable are we implying as the independent variable and which one would be the dependent variable? Very good. So in this case, a function of x, this is the independent one, and this is the dependent one. So the way we've written our equation is kind of in that standard form where the dependent variable is all by itself and then the independent variable is all on the other side, right? Okay. So does y equals x squared plus 2 represent a function in this case? Yeah, it should be easy to see that. Number one, you should recognize this as a specific kind of function that you studied last year. What kind of function is this? Quadratic, or even more generally, polynomial, right? So you know right away this is a function because it's of a form of something we know already is a function. But other than that, can you plug any value for x in and get a result? Of course, right? And if you plug a value for x in, are you guaranteed to just get a single result? Of course. So clearly this has to be a function. What if we reverse this, though? What if we ask if this is a function of, what if we define this as x as a function of y? No, right? So normally what you'd want to do is you'd want to rearrange this so that the dependent variable is by itself. So in this case now, x is our dependent variable and y is our independent variable. So we'd like subtract 2 from both sides and then square root both sides. And remember, when you square root both sides of an equation, that generates a plus or minus, right? So now here, if you pick almost any value of almost any value of y, that's the independent variable, how many values are you getting for x? 2, right? In almost all cases, right? What's the one case where you don't get two values? Well, when y is 2, right? When the square root has a 0 underneath it. But yes, exactly right. So this would not be a function in this case because for the most part, one input is giving you 2 outputs, right? And if it happens just one time, that's enough to say it's not a function, right? It doesn't have to happen like all the time like this one. We feel okay there? And that's the most common situation where you have a function or you have an equation and it's not going to represent a function, is that you can rearrange the independent or the dependent variable by itself and you end up with a plus or minus floating around in there. At least in a course like this. Yes, sir? Of course. Okay. A third way we can represent a function or relation is with a graph. Do you guys remember the way we check to see if something is a function by looking at its graph? Vertical line test, exactly. And what does the vertical line test say? Okay, perfect. So that's excellent. What if it's 3 times? Okay, so more than once would probably be a better way than twice. But although most of our cases would be just, it's hard to get one where you get, or define something where you have a bunch of intersections, but you could. So let's clean that up and make it a little bit more technical, although what you described is a perfectly reasonable working definition. It's going to work great for you in practice. So we say the vertical line test defines y as a function of x. So we need to be careful there because with what you're describing, Josh, right? Yeah. What Josh was describing assumes that x is the independent variable and y is the dependent variable, which is what we normally standardly do in our math classes, and it's not like we're going to violate that here. But if you're going to be precise, we should be precise and state that. If and only if, so remember the IFF abbreviation for if and only if. You probably talked about that in your geometry class. I'm breaking it out again. There is no vertical line that intersects the graph more than once. So a couple of examples here. And we'll just call these examples like A, B, and C. So for example A, is this a function? Definitely, right? Any vertical line you draw is just going to intersect the graph in one place. Doesn't matter where you draw it. Okay? How about B? Yes, right? Again, any vertical line we draw, it's going to get it just once. How about C? No, right? So I can draw a vertical line here, and it's going to intersect the graph more than once. Does it matter that there is a vertical line I can draw that it intersects the graph in just one place? No. Does it matter that there's a vertical line I can draw that doesn't intersect the graph at all? No. Okay. Let's say instead, for example, B, we have this graph that we're looking at plus this extra little point here. Is this a function? Not anymore, right? That little point ruined it because there's this vertical line we can draw that's going to go through the function and that little point and ruin things, right? Because now you're intersecting the function twice. Everybody okay with that idea? Okay. I'm going to erase that so when you go back and look at this, it's not, if you were to go back and look at it, it's not confusing. Okay. So you notice here that we were really careful when we describe these things as like, y is a function of x, and we have to be careful with our wording because it's not entirely clear if we just write an equation like y equals x squared plus 2, which one is the independent, which one is the dependent variable, right? We make the assumption that x is the independent and y is the dependent because that's kind of the natural convention, but there's nothing written in stone that says that must be the way it is. So one way we can be more clear about that is using function notation. And you guys remember what that is, right? Where instead of saying y equals, you say like f of x equals. Because now it's clear that the f of x is dependent on x, right? So we can clearly see that this is the independent variable. There's no ambiguity anymore. Everybody okay with that? The other advantage of function notation is it allows you to be a little bit more brief with some of your descriptions. So if I wanted the value of y when x equals 1, I have to write like a sentence. If I'm doing y equals 3x minus 4. If I have function notation, I can just write this. Everybody agree? So it helps us save in doing a lot of writing. It compacts the notation and allows us to express like an entire sentence with a single series of symbols, which is nice. Okay. So we feel good about telling the difference between functions and non-functions. I think you do a lot of that in the beginning of your Algebra 3-4 course. And then it's not that difficult once you've kind of figured it out. So hopefully it came back pretty quick. So the next thing that we're going to talk about is domain and range. And talking to fourth hour, they had given me the impression that when you wrote your domains and ranges last year, you primarily used interval notation to do that. Okay, so when we talk about interval notation right now, I'm not going to bother with all the little details. We'll just go to some examples and help refresh your memory, since it sounds like it's something you guys have already done quite a bit of. Is that okay? Okay. So I'm just going to write down some inequalities, and we're just going to translate these into intervals. Is everybody okay with that plan? To just kind of refresh our memory as to how we write out these interval notations. So the way I like to think about this when I write my interval notation is I like to first figure out what the upper bound and lower bound for the interval is, and then decide whether I should use a parenthesis or a bracket at each of those bounds. So if I have the inequality here, -5 is less than y, which is less than or equal to 10. What's the lower bound here, the smallest number involved? -5. And the upper bound is 10. The -5 should get a parenthesis or a bracket. Parenthesis. Why a parenthesis? Yeah, very good, because it's a strict less than inequality, not an or equal to. Very good. And then the 10 then should get a bracket. Excellent. We'll do just a couple more. But you guys seem pretty comfortable here, which is excellent. How about x is less than or equal to 2? This one, it's a little trickier. What's the lower bound? -infinity, right? There is no smallest number less than 2, but we use like that -infinity as our placeholder. For that, when there is no lower bound or no upper bound, we use -infinity or positive infinity, respectively. The upper bound here is 2. Very good. Now for the -infinity, parenthesis or bracket? Always parentheses for the infinities. Very good. And the 2 gets a bracket. Okay. And now for the tricky one, or trickiest one, I guess. So here we have an OR inequality. So a is less than -2, or a is greater than or equal to 5. Do you remember how you deal with an OR inequality in translating that to an interval? Yeah, very good. So we need the union symbol. That's that big U. Excellent. And then you can just write a separate interval for each of the two inequalities. So that's easy enough. For a is less than -2, the lower bound is -infinity, and the upper bound is -2. The negative infinity gets a, parenthesis, and the negative 2 gets a. Very good. And then for a is greater than or equal to 5, the lower bound is 5. The upper bound is positive infinity. The 5 gets a bracket, and the positive infinity gets a parenthesis. Now there's one more thing we probably should have done in each of these cases. So notice that this was not a list the domain or list the range where it's clear we're talking what variable we're talking about. And in here, each time the variable changed in these problems. So we should probably indicate here that like y is a member of this interval. This little symbol here, it's like a curvy E. Just means is a member of the set. Is really all that symbol is saying. So for the next one, because the variable we're using was x, we should probably say x is a member of that set. And for the last one, the variable that we were using was a, so we should probably say a is a member of that set. Just so we're very clear as to what's going on there. Is everybody okay with that? So instead of saying the domain is this interval, you could say x is a member of this interval and be done with it, because it's clear at that point we know the x's are the domains and the y's are the range. So you can use x is a member of and y is a member of instead of saying domain is this, range is this. And it's a little bit less writing. But it means the same thing. Okay. So we're going to talk now about domains and ranges. So one thing that's kind of seems tricky but is not is the idea of an implied domain versus a relevant domain. So the implied domain is the set of numbers that are algebraically possible from a given function. Oops. And a relevant domain is the set of numbers that logically fit based on the given situation. And in general, the relevant domain is always going to be no bigger than the implied domain. So we can say that the relevant domain is always going to be a subset of the implied domain. The symbol here that's like the sideways union symbol with the bar underneath is the symbol for a subset. And basically what this is saying is that everything in the relevant domain is also in the implied domain, but you could have things in the implied domain that are not in the relevant domain. So the implied domain is bigger, contains a little, possibly a little bit more, but it doesn't have to. They could be still the same size. And you're probably thinking to yourself, like, we haven't ever talked about this. This is new. And it's one of those things like we haven't spelt it out, but it's not a new idea, I promise. So the implied domain, unless there's like a story problem context, is just all real numbers, right? In an algebra class, in a high school setting, you're working on the real numbers, right? That's the stuff that we're using to do our algebra with. So unless you're in a story problem setting where it doesn't make sense to have negatives or 0 or decimals or something, the relevant domain is just all real numbers. Okay with that idea? Now, if you're talking about a story problem where the variables involved are like the lengths of something, negatives don't make any sense in that context, right? So in that case, the implied domain would just be, the non-negative, or maybe 0 doesn't even make sense depending on the context. Maybe it's just the positives. Or maybe your story problem is involving like the number of people that can fit in a car, in which case negatives don't make sense and decimals don't make sense. You can't fit half of a person in a car. Unless you're like an axe murderer or something, like, I don't want to count anybody out here. I know what you're capable of. That's a joke. You can't see I'm smiling under the mask, but I'm trying. Does everybody get the idea with this implied domain? Is that it's really just all real numbers unless there's some story problem context that would say, oh yeah, like a decimal doesn't make sense in this situation, or a negative can't make sense here. The relevant domain is going to be like what you did when you talked about like rational functions, where you actually have to look at the type of function and go, okay, what values of x would make this thing undefined, right? Is everybody okay with that plan? So we'll do a couple examples here to kind of help clarify this. Okay, so our first example, f of x is equal to 2 times the square root of x minus 4. So there's no story problem context here, so the relevant domain is just all real numbers, right? It's just like an algebra problem. We can just assume it's all real numbers. Now, because we have a square root function, what do we have to be careful about? Yeah, we have to worry about positive and negative underneath the square root, right? So the only place where the square root is going to be defined is when the stuff under the square root is greater than or equal to 0, right? We can take the square root of those things, but if they're negative, we can't. So the things that we care about have to be non-negative, greater than or equal to 0. So I can then solve this inequality just by adding 4 to both sides. And then I can translate this inequality into an interval. And there's my implied domain. Yes, sir? No, I usually just do it for clarity. Yeah. If you, instead of positive infinity, you can just write infinity. You need the negative on the negative one, but you don't need to put the positive on the positive one. Yep, that's fine. So just notice here that this interval, 4 to positive infinity, is a subset of negative infinity to positive infinity, right? Everything in 4 to positive infinity is included in the above one, but there is some stuff in the above that's not in the, or in the relevant domain that's not in the implied domain. Everybody see that? Okay. Let's do another one real quick. Okay. So here we have a rational function. Again, we're given no context of this, so we can just assume that the relevant domain is all real numbers. I'm sorry. I meant the implied domain. Did I do that up here? I did do it up here. You know what? It's early, guys. This should be implied domain. This should be relevant domain. Goodness gracious. If you see me making a mistake, please speak up, or if you're not sure, like, do you have those two switched? Even if you're wrong, that's okay. Like, say something. You're probably not the only one wondering, you know. And if I'm making a mistake, please stop me. Okay? And if you don't catch it, that's fine. I get it. A lot of times I'll come back and catch it, but it's particularly those of us that are like just trying to pay attention often catch these things and don't say anything. Please say something if you see me screwing up. Or even if you're not sure if I'm screwing up, like we'll take a minute and double check. It's okay. Okay. So for B, this type of function is a rational function, right? Where is the place where we can get into trouble with rational functions? When the denominator becomes 0. So that's what we have to worry about here. So I know that anything other than when the denominator is 0 is going to give us a value in our domain. So I can solve for this by subtracting 2 from both sides. But now I need to translate this not equals to equation into an inequality. Well, I'm actually going to need to use an or inequality to deal with this, because x not equal to 2 means that x either has to be less than -2 or greater than -2. Everybody agree with that? That that's going to mean logically the same thing as not equal to? And now that I have it recast as an inequality, it's easy enough to rewrite this as an or interval. Is everybody okay with what we did there? Okay. Good. Good. Okay. Our last example here, we have v of s is equal to s cubed, where v of s is the volume of a cube, and s is the edge length of that cube. In this case, the implied domain is not all real numbers, because we have some context applied here. So if we're talking about the edge lengths of the cube, what are reasonable values for the possible edge lengths of a cube? Yeah, they have to be positive numbers greater than 0, right? You can have decimals. You could have half an inch side. That's fine. But you can't have 0, because if you had a 0 length cube, I think you just have a point, and I don't think I would define that as a cube. And you certainly can't have negative. Negative length makes no sense, right? So here, our implied domain would be 0 to positive infinity, all the positive numbers. Now, if I look at this function here, s cubed is what kind of function? Cubic or polynomial. Can I get in trouble plugging things into a polynomial? No, right? Never. So the relevant domain is going to be still the same thing as the implied domain, right? I can take any of those positive numbers, plug them into s cubed, and it'll spit out another value, right? It's impossible to get anything undefined here. Everybody's okay with that? So in this case, there is no subset relationship. They're exactly the same thing. I mean, depending on how you define your subset, like The same is still a subset, but that's getting beyond the scope of what we need to deal with here. Okay. What if we want to go back and find the ranges for these? So there's a couple of ways that you could attack something like this. But the ranges typically are more difficult to find than the domains are. Why do we say that? Because it's a dependent variable. It depends on what the domain is. The domain doesn't depend on anything. It's independent. So you can find the domain right away with no other information. To find the range, you often need the domain in order to kind of do that. Everybody's okay with that idea? So I'm going to talk about a couple of different ways you could kind of conceptually think about these. Now this one, if you remember back from algebra last year, we know that this is a square root function. And the standard form for a square root function looked like this, right? And maybe we remember that the domain then was h to positive infinity, and the range was k to positive infinity. You might remember that. It's possible. I'm sure you did this or saw this rule last year. Or maybe you didn't, based on some of the faces I'm seeing. Maybe that's new. I don't know. But right away that would tell me then that in our case, since I have nothing out here, my range would be 0 to positive infinity. Now let's pretend we didn't notice this. Okay? Another way we could think about finding a range would be to basically kind of use this idea of inverses. Kind of. So when we found an inverse for a function like this, what we did was we started by trying to get the x variable by itself, right? So the first step we'd want to do is dividing by 2. Right? You kind of remember this when you found inverses last year? I'm seeing some head nods here. Now what would you want to do? Square both sides, right? Which is perfectly reasonable to think to do. What's the problem with doing that, though? We'll write it down so that what was our problem when we squared both sides here? What values of x can I plug into this? All real numbers, right? What values of x can I plug into that? Not the same thing, right? So here, when we do this, we have to also make sure that we're saying where x is greater than or equal to 4. This was from the domain, right? Everybody agree with that? Okay. So, if I look at this side, And these are the x's I can plug in. What's the smallest x I could plug in? 4, right? Everybody agree with that? When I do that, what value of y do I get? 0, right? So 4 minus 4 is 0, so I have y squared over 4 equals 0. You can multiply both sides by 4, still 0. Square root both sides, still 0. Y is 0. Now, if I think about x squared, the graph of, the graph of x squared plus 4, that graph is like always increasing, right? Particularly if we're starting from the x value of 4, right? So I know then this, should say this is our minimum y value, right? And because our x's can keep getting bigger and bigger and bigger, so will our y's with the rearrangement we've done. So basically I know as x goes to infinity, y goes to infinity. And I can say, okay, well, we're just going 0 to positive infinity. Before there made no sense. And that's a perfectly reasonable way to kind of approach it. But probably the most practical way of approaching this would be to look at the graph on your calculator. If this emulator wants to open for me. I've had the devil of a time getting this thing to actually do what I want it to. All right, well, it seems like it's going to be stubborn, so I'm going to skip it and do it with Graphmatica. Evan, will you grab the light for us? I know with the dark background on Graphmatica, it's hard to see on the projector with the lights on in the room. Thank you. Is it still light enough in here for you guys to see your sheets? Okay. That may change by February, but so I'm just going to kind of type in my function, or if you could do this on your graphing calculator. For whatever reason, my emulator is being stubborn and it wasn't working yesterday, and I haven't got a chance to look into it today. But this is Graphmatica. It does the same thing that your graphing calculator will do. So we can see right away, here's our function. The minimum y value appears to be 0, right? This is the lowest point at 4, 0, so the minimum y is 0. And it continues to grow and grow and grow and grow forever without bound, right? Because we can plug any x value in we want greater than 4. The bigger the x, the bigger the y is going to be, right? Which should make sense. The square root function is an increasing function. Like if I take 2 and 3, 3 is bigger than 2. I'd expect the square root of 3 to be bigger than the square root of 2, right? That's how the square root function behaves. So I know it's increasing the whole way through, so we can go 0 to positive infinity. Is everybody okay with that idea? So in general, for the ranges, it doesn't much matter to me which approach you take. Any of them are perfectly reasonable approaches. Let's do one more. And kind of talk through some different ways we could approach this one. So from your Algebra 4 class last year, we recognize this as a rational function. And we recognize this actually as the as one of the forms for a simple rational function, right? This was one of the ways you could represent a simple rational function. And we know the domain was, in this case, like x not equal to negative d over c. And the range in this case was y not equal to a over c. So we can say in our case then, it's 3 over 1. So I know that my range is negative infinity to 3, union 3 to positive infinity. You guys remember doing that at all last year? Might have been towards the end of the semester, whatever. Rational functions tend to be one of the last things we get to in that class. But the fact that this was a simple rational function made life a little bit easier. If it was a general rational function, much, much harder to come up with the range on those things, and there's not really a good predictable way to do that, unfortunately. Okay. The other way you could approach this is thinking about it like an inverse. So if I want to find the inverse to this, I want to get the x by itself, right? So I'm going to start by doing like a cross multiplication. So I have 3x times 1 equals y times x plus 2. And then we'll distribute that y through. And then I'm going to move all the x's onto one side. And then I can factor an x off, because there's an x in common with each. And then I can divide both sides by that 3 minus y. And now the x is by itself. Right? So what I'm going to do is look at this piece that has only y's in it. This is a rational expression, right? Where do rational expressions run into problems? When the denominator is equal to 0. So I know that 3 minus y can't equal 0. And that's going to lead us to that same range that we saw earlier. Everybody okay there? Now this was a little bit sneakier, some of the algebra I used to kind of get that x by itself when we found the inverse. Maybe if you hadn't seen that done before, you might have gotten a little tripped up on what to do there. But having done it once or twice, it's not really that difficult, but it's cross-multiplying and then having to do the factor and divide by a quantity is maybe not the first thing you'd be thinking of in this kind of a problem. But once you've seen it, you're like, oh, okay, I can deal with something like that again, hopefully. Or we could always look at the graph. So if I just did y equals 3x divided by x plus 2, and probably zoom out a little bit. Should be relatively easy to see that there's a horizontal asymptote going on here, which is going to be the only y value that we're going to have to throw out of our range. And it looks like y equals 3. If I type in y equals 3, I'm pretty convinced that's your horizontal asymptote at that point, just by looking at the picture. Is that okay with you guys?